Yeah, I guess that's it. Welcome to the first ever episode of the RockyTerrain podcast. After a long time of planning and trying to figure things out and trying to fix technical problems, here we finally are. My name is Thomas, and with me today, and hopefully for the future, is my very good friend Dennis.
Yes, I hope so too, because we've really been thinking about getting into SciComm for a long time now, because it's something we are both really, really passionate about. And yeah, we've been thinking about podcasting, about maybe making videos on YouTube, all kinds of stuff. And since we both really, really enjoy talking about science, natural sciences, scientific theory, and all kinds of things of that nature, why not press the record button and hope that someone will enjoy listening to it?
Yeah, I mean, we both just love to talk hours and hours about, well, science and our topics, and I think starting with a podcast is a very good idea here because we can just express ourselves, and even if nobody's listening to, we still have some way to communicate with the outer world.
Yeah, it's essentially, I mean, I see it as some kind of an outlet because, as already said, we both would like to get into SciComm, and we have different things planned for the future. Like, for instance, we would like to center this whole podcast around earth sciences, geosciences, because that's the field we're both active in, and maybe we will conduct some interviews with people from our university, trying to give an inside perspective to what people in this field of research are doing, and we don't know. We will see where it goes.
Yeah, I mean, there are a lot of podcasts these days. I guess I literally could stop anything I'm doing right now and just listen to podcasts my whole life, and I would have never a moment where I don't have any podcasts left. Still, the field of, well, earth sciences or geosciences is, in our opinion, still, well, there are not that many podcasts talking about this field. There are a lot of very good science podcasts, and then there are podcasts, for example, about paleontology that we both really love. But this whole field, this earth science field, which is really large, and we are going to talk about this later, there's still not that many, well, podcasts or videos about this. So yeah, we hopefully here find our way into this niche, and maybe, well, people will like this.
Yeah, and another thought also is to, I mean, we're both still bachelor students, so we've just really started getting into academia, and the thought is to maybe try and give a student perspective into these things, and to see how, maybe we will like to listen back to this ourselves, try to see how our perspective on things changes, to observe our way through academia, and to see how hopefully we grow on different tasks.
Hopefully grew on this podcasting stuff, because you don't want to know how many tries we did before.
Oh, yeah. I mean, we're both no native English speakers, so please bear with us. And additionally, we're both doing something like that for the very, very first time in our lives.
Yeah, this is our first steps into the SciComm field.
Yeah.
And you have to grow on this. There's nothing you can do like out of the nowhere.
Yeah, you're pretty nervous. It's this completely new situation, sitting in front of a mic, trying to convey ideas in a different language. I mean, I hope we'll do okay. We probably won't, but I hope we'll do okay.
There's a try.
Yeah, I mean, but First things first, Thomas.
Yeah.
I think we should start with introducing ourselves and tell me, who the hell are you?
Yeah, why am I even here? This is a very interesting question, Dennis, and very convenient to ask this in our very first podcast. Like it was planned.
Like it was planned, indeed.
All right, so let me tell you a story of myself, because people are probably really interested in my personal life. Probably not, but you have to listen to it anyway because it's our podcast. Yeah, so I'm from a very small town in Bavaria, and actually the first memories there, well, somewhere in my head are about dinosaurs. And my parents and friends and probably all other people that know me back then always tell me that I was really into dinosaurs. And I mean, like, I was not interested into dinosaurs, I was really into dinosaurs. I was that kind of a child. My parents always tell me that before I even could speak, I would just run in our house and just try to be a dinosaur and try to tell them anything about volcanoes and T-Rex and other dinosaurs. I really was into this. And actually this grew for a really long period of my time, and this shaped my path for the future. And even in elementary school and later, I always wanted to go into sciences, and I always wanted to study paleontology, so the study that studies dinosaurs, basically.
Extinct life, Thomas.
Yeah, extinct life, dead animals. Yeah, but I ended up on some kind of a different path here, but let me try to explain this. Later in school, there's a time where you try to search for new interests and where you try to figure things out and, well, just try to imagine your later life. In this time, I thought about a lot of things, for example, architecture, but I don't know, just the idea of science was always kind of my plan A. Later in school, I grew a large interest in astronomy and the field of space exploration. But I was really bad at school, not really bad at school, but I wasn't that good at school, and I had especially problems in physics, so studying astronomy always seemed very far away. Then after school, I had to take a break, so I didn't do anything for a year, or well, didn't do anything, but I worked, and I tried to figure things out, what I really wanted to do with my life. And well, my interest in astronomy grew, and on the same time, I know that astronomy wasn't something I could study. So I wanted to study geosciences, earth sciences, and then later become a paleontologist. But in this year, I actually found that there is a very specific niche where I could combine some of my interests, and this is planetary science. So I could still study earth sciences and then try to figure different planets or try to study different planets. And this idea really grew on me, and I tried to search where I can study this, and it's very niche, so there are not many universities in Germany that actually allow you to study this field. There are actually 2 universities at this moment, and this is Munich and Münster. Now, Munich is very close to my hometown. I could basically take the train in the morning and then came back in the evening. And then there's Münster, which is 500 to 600 kilometers away from my hometown. And well, I ended up moving to Münster. This was a decision I did in, I guess, 2 weeks before university began. I just liked the university in Münster more, and I thought this was a better path for me, and I thought maybe it's a very good decision. And well, here I am. This was now 3 years ago, actually. And I guess this was one of the best decisions I've ever made in my life. I love the city. I really love our university. And I really love the field that we study. I'm currently writing on my bachelor thesis. So I will study my master, or I will go to master studies next month after I finish my bachelor thesis. And this bachelor thesis is actually already about planetary sciences. I work on this project, or not on this direct project, but I work in our Institute for Planetary Sciences now since over a year ago. And, well, I just learned this is really my dream. This is really what I wanted to do for my future. And this is where I am now. My whole study in the moment for my bachelor thesis is about lunar tectonics, which itself probably could fill an entire podcast, and which we will talk about later and in future podcasts, but just maybe for a simple, small introduction to this topic. Lunar or lunar tectonics means I look at tectonics on the moon, and tectonics are the study of the movements in Earth crusts or on other planetary crusts. We know on Earth there's mountain formation, there are earthquakes, we have tectonic plates movement, and there's a lot of stuff going on Earth, but not entirely on Earth. We have similar processes on other planetary bodies too, like, for example, on the moon. And this is what I'm studying at the moment. And I guess I will talk about it in a later podcast, probably after I finish my bachelor thesis, and maybe even, write a paper about this. I don't know yet. Yeah, that's where I am now. This was a long introduction. Anyway, I just asked you the same question, Dennis. Why are you here and what are you even doing?
Yeah, glad you asked. My name is Dennis Teda. I was born in Germany as well, but in northern Germany, in North Rhine-Westphalia. And in that regard, we're pretty similar, because I don't even remember a time before dinosaurs were a part of my life. They've been with me ever since I can remember. And ever since I can remember, I wanted to become a paleontologist. When I got older and got into school, I really, really, really dreamed of getting into academia. But, to be quite honest, I wasn't really too good at school. At first I was, but, 7th and 8th grade, I really wasn't good at school during that time. And getting into natural sciences really seemed very far away at the time. However, when I had to make the decision whether to get professional training or to make my A-level, I decided to make my A-level, because essentially I didn't really know what to do with my life yet. And I'm very glad I made that decision, because one of my main subjects, my core subjects during my A-level was biology. And it was in biology class that my fascination and my passion for evolution and for the history of life really, really came back and grew stronger than ever before. And it really went as far as me having the feeling that I would really, really, really regret it if I didn't give it a shot and didn't try to become a paleontologist. Yeah, so that's the decision I made. I decided to go all in, and I researched how I could become a paleontologist, and turns out there are two ways. One is via biology. You start studying biology and then you really focus on evolutionary biology. The other way is geology, geosciences, earth sciences. in Germany you can study paleontology as its own subject. It's a part of these two disciplines, biology or geology. And I don't know, I always was very fascinated by biology, so I thought, I don't know anything about geology, let's go with geology. Yeah, and I've chosen Münster because this town wasn't very far away from where I lived at the time, only about a 2 hours drive. And I knew that the university here in Münster cooperates with a museum I've loved ever since I was a little child. And so I decided to go here, to go study in Münster, and things turn out pretty well because right now I'm having a job at the museum where I help out at a dig site, a lower Cretaceous dig site. And my plan is to go to the University of Bonn to make my master's degree there, because that's really the place to be for vertebrate paleontology in Germany.
Yeah, and I guess you will tell us about your things you're working on in a later podcast, probably. Yeah, it's a very interesting topic, and I'm really looking forward to you talking about it. So, now you have information about two random dudes from the internet that just told you a life story because of some reason.
Yeah. I don't know. Yeah. I just felt like it.
No. So now you know us, and you know maybe some of the reasons why we're doing this podcast, and why we're so interested in this topic. Now, we are both still bachelor students. We've already told you this. And so we really try to always research what we're going to say. This is really, really important for us. And we only want to talk about stuff that we really understand. So we really try not to do any mistakes here. And yeah, the scientific process and the scientific theory is really important for us.
Yeah, indeed. I think it's a great opportunity for us to really grow as scientists and as honest skeptics, I think. That's at least what my vision for this whole project would be.
So I think the interesting question that we have to ask ourselves here is, how can two people study the same thing and end up doing completely different things? And for that, we have to ask ourselves, well, what are actually earth sciences all about? And therefore, I guess, that's this be the first topic of our podcast. Dennis, so I'm just going to ask you, what are actually earth sciences? Can you give us a small definition or a small introduction to this topic?
So essentially, what people in earth sciences are doing is try to use all other natural sciences to explain how the earth system works. You know, the earth is a rocky planet which has all kinds of different processes going on all the time. You know, you have, for instance, tectonics. You have interacting layers of the earth reshaping this planet all the time, which is driven to a large degree, at least, by very complex chemical processes inside Earth. And then we have biology. How does Earth interact with life? And in turn, how does life change when Earth changes? So essentially, we use all kinds of natural sciences to work out what Earth is all about. But this field isn't restricted to Earth necessarily, because other rocky planets are a subject of interest as well. Like, for instance, you guys in planetary sciences, you guys try to figure out how do other planets work. You take what we observe on Earth and try to see whether it works the same way on different other planets, or whether it works differently there.
Yeah, I like to think about the Earth or other planets as these machineries that have all these different gears, and all these gears have different shapes and sizes, and the number of these small little teeth on every gear are different, and the forms of these teeth are different. But it's still working, and everything is kind of connected to each other, and changes in one of these gears can have influences on the whole machinery and the whole subject. And this is with every planet the case. I mean, all the planets have different gears, if you want to stay at this explanation, but still they all work on the same natural principles that we can also observe here on Earth. And so trying to understand this machinery and trying to understand these processes in these machineries is basically what Earth sciences is all about. And I just love this. It's so amazing to have all these different fields come together. It's chemistry, physics, as you said, and biology, and you just try to figure out, wait, what is a planet actually, and what is happening here? And yeah, it's really amazing. Really amazing.
Yeah, I really think that's the wonderful thing about studying Earth sciences. Because, we both started with certain expectations. You wanted to get into planetology or planetary sciences. I wanted to get into paleontology, but along the way you encounter all kinds of different subjects. I mean, we both stuck with what we came here to study, to learn about. We stuck with our particular fields, but you encounter all these different interesting aspects about Earth sciences. For instance, you encounter subjects like historical geology, trying to reconstruct the history of this entire planet, how it has changed over the millions of years of its existence, the billions of years of its existence.
Yeah, and if you look at the Earth's history, if you want to stay on this topic, I mean, there's so many things to unravel here. We can talk about, well, the formation of the Earth itself, or if we even go farther, the formation of our solar system, because in the end, this is also what geoscience or Earth sciences are talking about. If you want to look at geochemistry, for example, this is also something that our institute is working on, to understand these processes in this solar nebula and how planets are even forming. So you have chemistry here, which tells you, for example, about the element attribution or the element abundances in the solar nebula, but you also have physics, which explain you all these different processes involving gravity in the solar nebula. And then you have planet formation, and how does this even work? Why are all our planets different? Why has Mercury, for example, such a large iron core? Why? And why Earth not? Then we have a large moon. Why do we have such a large moon? Which is actually a topic I want to talk about in a later podcast, because this is a very interesting topic.
Yeah.
And then we can, yeah. So it starts from the beginning of our solar system. So the word Earth sciences, I mean, there was no Earth back then. But it just still was on the way on this first, the first things that happened in the solar nebula had influences on our planets and on Earth itself. So we have to start so early at the beginning to, try to understand Earth.
Yeah. And the interesting thing here is that this is, I think, what people often don't realize, that at these time scales, it's difficult to even reconstruct what happened back then, because we in this field of research we use rocks as essentially our record. We are looking at rocks and try to figure out what exactly happened back in the day. We date rocks, we look at their nature, because there are different kinds of rocks. Not all rocks are the same. You have, for instance, magmatic rocks, which are essentially just what happens when a melt, when lava, magma cools down, hardens out, and becomes rocky. And when these rocks eventually harden out, what happened on early Earth? Early Earth slowly cooled down, slowly hard elements started forming. These rocks start to break apart, to erode away. And when these tiny little chips of rocks, the sediment which results from all these processes, is redeposited, sedimentary rocks are formed. Then, in turn, for instance, we've talked about tectonics earlier. The shape of Earth, it keeps changing, plates on Earth keep moving. You can also form metamorphic rocks, rocks of sedimentary or magmatic nature, which are essentially completely deformed by these forces. And this is what we are trying to use. We are trying to look at the rocks of the different periods of our Earth and try to puzzle together how everything came to be the way it is. Starting with a very, very nebulous beginning, the formation of early Earth. I don't even know, do we really have rocks from early Earth? Do you know that? From the earliest parts?
Yeah, the question is, first of all, what you define as rock. But the first material, I guess, that we have from Earth itself are the Jack Hills zircons.
Yeah.
I think they're the oldest at the moment, but, there are new finds every time. So these are small minerals, so zircons are small minerals. These were in early magmatic rocks, as you said before. And then they were well transported and probably even recycled, which means that they went into the into the Earth's mantle and then came back later. But still, these small minerals, which are very strong and they don't erode very fast. In these small minerals, we have actually we can date them. I think dating stones or minerals is a very interesting topic for later too. But in these small minerals, there are small material, which is about, I guess, 4.3 or 4.4 billion years old. Hi guys. Thomas from the future here. I'm just going to interrupt you for a sec. I've realized that I said stones all the time for the next minutes. Of course, I meant rocks, not stones. There's a difference. And I'm really annoyed by it now, so I'm just going to interrupt you for a sec and make that clear. Well, thanks. Have fun with the podcast, guys. Now, if we talk about first stones, I guess the first stones, and now this is going to be difficult to spell, Nuwagituk. It works. Nuwagituk greenstones.
It's horrendous when you have to write an accent.
There are about 4
different rocks. These names are pretty difficult to spell out.
Yeah. Yeah, so they're from Canada, from Quebec, and they are about 4.28 billion years old. Now, they are not volcanic stones, actually, and these are not minerals, these are real stones. They are volcanic stones in some way, but these are metamorphic stones, which means that the stone itself get later, it later evolved farther So there were strong forces, for example, heat or movement through mountain building, mountain formation. And then through these strong forces, the rock was morphed into a new version of the stone. And, well, these are the stones that we have with the new Architect greenstones, and they're 4.28 billion years old. So these are like the oldest stones we have of Earth. And the oldest, the oldest views or the oldest windows that we have into early Earth. Because, as you said before, stones are the tool for us to look back in time. Because there's no other way to look back in time in the small scale on Earth or in our solar system. This is actually what it's all about. We can look at meteorites, for example, if you want to go farther even. If you want to look much earlier on Earth, there are meteorites, for example, that contains small amounts of solar dust that was part of this nebula. And then there's also dust particles that we know are even older than our solar nebula. So, and all preserved in stones here on Earth and, well, outside of Earth too. But let's stay on Earth here. I'm just getting carried away.
Yeah, you are, but...
So these are the oldest stones we have. Yeah.
It's pretty fascinating. That's the thing that's the thing why we started a podcast in the first place, because we like to get carried away.
Yeah. And this topic is really inviting you to just get carried away and talk about a lot of different things. But if you want to stay on Earth, so now we know we have these very old stones, these very old rocks of Earth, but there's one more thing that really defined Earth in the beginning, and actually very early in the beginning of Earth's history, and this is life. So, Dennis, I don't know if you have the numbers in that, because I don't, and I have not written them in my little notebook here. Do you know when the oldest fossils, so the oldest real fossils or traces of life, when did they form?
Numbers do keep fluctuating.
Yeah.
To be honest, the oldest life must have popped up pretty early. So, numbers are changing and changing and changing. But we seem to keep pushing this, let's say, from the top of my head, 3.5, 3.6 billion years, where some kinds of organisms seem to be present in rocks. And this is essentially where paleontology starts, for example. And this is really the first time that this discipline becomes relevant, because paleontology is what deals with extinct life. We start to see that organisms appear and that they start to interact with the Earth system. Earth, it forms. Over time, an atmosphere is generated, which is probably also an interesting topic for the future. How does an atmosphere form?
Oh, yeah.
Yeah. And I'm more of a vertebrate paleontologist, so I can't really say too much about these early periods, but I think it's pretty safe to say that these early organisms, they should have interacted with chemical vents of some sort. So, deep inside our oceans, below the waves, we have spreading zones, where new lithosphere is generated. Oceanic crust is generated. Think, for example, the mid-ocean ridge in the Atlantic. And there you have hydrothermal vents where heated fluids, heated by, the magmatic activity below the crust, get vented out. We often tend to think that life was generated down there, that, organic compounds started interacting there, launching an ever more complex chain of what we would now describe as organic chemical reactions. What we can see then is a period of very, very, very primitive life. A large time of Earth's history, we didn't really have complex organisms. We stay with bacteria, we stay with single-celled organisms, and despite that, we can see that organisms interact with Earth, interact with the atmosphere. For instance, in historical geology, you can show that they took CO2 from the atmosphere because some of these organisms photosynthesized and started to lay down organic layers in marine environments. And this is really where one could say this new era had begun, this new era where this new factor of biology started actively shaping how Earth transformed, because as we today know, CO2 is a very, very important compound in our atmosphere because it's very, very important to regulating how much sunlight is reflected off into space, or is, if we have a lot of CO2, bounced back to Earth's surface.
I love the fact that oxygen is so important for life today, but the reason that we even have this much oxygen in our atmosphere is probably life itself.
Yeah, so indeed. We had organisms.
Life built its own future.
Exactly. It's life paving the way for other life. And we're talking a lot about historical geology now. So we're talking about really trying to figure out how Earth developed. But we've touched on this. We already do have some aspects of planetary science because we want to figure out how planets evolve, and our best sample for this purpose is Earth because we live on Earth. We have, general petrology. Petrology being basically this field which tries to figure out how rocks are formed, which is via magmatic processes, via sedimentary processes. There we have sedimentology come in, how are sedimentary rocks formed, deposited. And so even in early Earth, we can already say we need multiple disciplines to try and figure out how this very, very early system worked. But essentially, at these times, at these ages, we're pretty limited because let's talk again about tectonics and plate movement. Most of these rocks get lost over time, and we don't really have too many rocks from these ages.
Not on Earth, at least.
Not on Earth, exactly, because, little spoiler, plate tectonics isn't really much of a thing in the grand scheme of things.
Yeah, I mean, Earth is our best, study scenario here because, as you said, we live on Earth. But actually, Earth is kind of the odd one out if we look at all the terrestrial planets in our solar system. We have no plate tectonics even on Venus, which basically is the same size of Earth. And the question is why? Why does only Earth has plate tectonics, while Venus don't, for example? Earth seems to be the odd one out here.
Yeah, and this is actually a pretty interesting topic because we don't understand why plate tectonics aren't really present on other planets. And here, back on Earth, it's a very, very complicated field. there are many different aspects which contribute to why we even know that plate tectonics are a thing. I mean, for instance, we've already talked about mid-ocean ridges where new crust is formed. On the other hand, we have subduction zones, like, for example, in the Pacific, where oceanic crust is subducted. You know, it dives down back into the earth to be molten up again. We know that on the one hand, new crust is produced. On the other hand, crust is destroyed, which must result in movement. And we have evidence for extensive movement in the Earth's past, like, for example, geographical evidence. Geography tries to explain where everything on Earth is and why it is where it is. We can, for example, say that South America and Africa, they seem to fit together pretty well, which is maybe not convincing evidence, but it's intriguing. And from Earth's past, we have fossils which appear on different continents today, and the easiest explanation would be that these habitats where these animals used to live once were closer together. This is the easiest way to explain why fossils do appear on completely different continents. One example would be the example of Mesosaurus, an aquatic reptile from the Permian, which was found in several different continents. And this just goes to show how many disciplines really contribute to figuring something like that out. And this is just the surface of all of this.
Yeah, when we talk about plate tectonics, there's a lot more than we can talk about. There's mountain formation, for example.
Oh, yeah,
we have mountains
indeed.
here in Germany, the Alps. Actually, we have mountains on every continent. And mountains itself, this summer, actually, we were in Swiss for a week for university. We did a field trip there to try to understand a very special small part about mountain formation. Now, first of all, I was really lucky this was even possible because of the current coronavirus situation, but travel in Europe is actually already allowed. So yeah, there were some plans how to do this, but in the end I was actually happy that it was possible. And actually I was in the Alps so many times as a children. As I said before, I came from a small town in Bavaria, and I guess it's like 1 to 2 hours drive to the Alps. So I was there to ski or just there for an afternoon or something like that. But since this time now, since this 1 week, I see the mountains in a completely different way than I've before. These incredible forces that played there, these incredible forces that created folds that are kilometers in scale.
Yeah.
It's incredible.
Absolutely.
I remember we were on this, it was next to a small street, and it was just a few rocks laying on the side of the street. And we looked at these rocks, and it was possible to see small minerals in these rocks that were deformed. And these deformed minerals can actually give you a clue about the movement in this rocks before. So we looked at the small stones and rocks there, and we said, there has to be a movement to southwest, I guess. And then at one point, our professor just said, now turn around and look at these mountains. And we looked at these large mountains, and in these mountains, we actually saw evidence for this south-trended movement. Completely blew my mind. Completely.
Yeah, I've been to the Alps as well, just a few days back, actually, not even a week, because I've been to northern Italy. We just drove through the Alps. We didn't really stop there, except for photographs. But It's really impressive. I mean, the Alps, they result from the collision of Europe, Eurasia with Africa, and sometimes it's really, really difficult to wrap your head around just the sheer dimensions, how extensive, how colossal such a collision truly is. Another famous case of such a collision is the Himalaya, where India collided with Asia. And we know that there must have been a collision starting, I think it's about late Cretaceous age, early Cenozoic. Do you know about that? Yeah, and
movements.
It's still going on today. You can look at the rocks inside the collision zone, inside the Himalaya, and you can basically interpret the way these rocks were deformed from where the collision came. And this is a really, really excruciating task because these structures, mountain ranges, they can be really complex on the inside.
If you look actually, for example, for Mount Everest, we know that the peak of Mount Everest itself is actually made of a different material, of different rock than the basement of Mount Everest. So there's actually, in Mount Everest itself, there's a thrust fault exposed that moves through the whole Himalaya range.
So you can basically say that there must have been a very, very extensive deformation of the crust. And of course, this is not observable in a lifetime, for instance.
Yeah, the ages we talk about in earth sciences are different than the ages that we perceive as humans. And this is something you have to wrap around your head before or in this process of learning or going into earth sciences. For example, when we talk about young, I guess for me, young is everything, younger than 60 million years, I guess. 60 million years.
Yeah. I mean, the age of mammals then all of a sudden seems pretty close, because when we talk about basically geological time ranges, we're talking about tens of millions and millions and millions of years. And I think this is really something you start to just accept over time. And sometimes, you have these moments where you're looking at these numbers and where you realize what kind of an hellishly long time period this is. It's just, you just stop thinking about it one day, because it's really, really difficult to wrap your head around it, I guess.
You became some sort of dull, actually. It just
accepting.
You hear all these ages. 4 billion years. Yeah, okay. And 4 billion years. Just try to imagine this number.
Yeah, but then again, this is something I think this is something I really enjoyed during, the Earth history course. You just go through Earth's history and you start to really understand, as you do in our field of research in geosciences, earth sciences, how long things take, how long time periods of relative stability actually last. I mean, what we are talking about, the formation of mountain ranges, these are tens of millions of years. The formation of oceans, tens of millions of years. I mean, for instance, just think about the opening of the Atlantic Ocean, which has been going on ever since about the early Jurassic is where we have the first signs of it opening up, which is about at least something like 200 million years ago. And it still keeps opening up till this very day.
Yeah, I mean, this is actually something that I think is a difficulty if you try to speak with other people that are not in this field of earth sciences about geology or earth's history, because there seems always to be this disconnect when you talk about these timescales.
Yeah.
For us humans, earth seems very stable. Like, nothing changes really. It's always the same. But it's just not the case. Earth is so changing, and
that's what we're
so different.
That's what we are experiencing right now. You know, we have short-term fluctuations, which we often tend to, I think, ignore, because we have had these short-term fluctuations during the existence of, you know, true civilization. Like, take for example, you know, cold periods. I remember vividly how our paleobotanist professor told us about one very, very short minor, he called it miniature ice age in the early 1940s, the time when Germany tried to invade Soviet Russia, the Soviet Union back then, where actually the temperature seems to have been going down for some years. Ever since then, it's been reheating up, as far as I know. I mean, now especially, we have an upward trend. But this is something we sometimes tend to ignore, I think.
Yeah, and I mean, if we already talk about climate and this upward trend in temperature, then we also have to talk about climate change, and especially human-introduced climate change that we face currently, which is also in the field of earth sciences. Because, and I think this is really mind-boggling for me, because people always say, or not people always say, but many of these climate change deniers, they always came with this argument, but Earth had temperature fluctuations in his history too. We had times where there was much more CO2 and it was much more hotter. But so why should we worry now? And I'm thinking, that's exactly why we are worried, because we know that Earth experienced this before, and we know how different Earth was back then.
Oh yeah, indeed.
We know that, for example, I guess 60 to 100 million years ago, Earth was a lot hotter. But also we know that the sea level was much higher back then. It was a completely different world for us.
Indeed, and that's the thing. Earth will be fine. Earth will be fine. Life on Earth will be fine eventually. The question is, what about us? And this is maybe where we could transition into applied geosciences, because there is a huge niche of geosciences dealing with the influence of humanity on this whole Earth system, and on the other hand, dealing with how can we use this Earth system for our benefit.
Applied geoscience, even if it's not like the field that I'm most interested in, or a field that I would want to work in, just because I like the natural sciences a bit more. But it's so important for our future. It's so important. We talked about climate change before. It's so important to understand climate change and to see what we can do against it. It's important. I mean, we live in a society where nearly every one of us has smartphones, for example. And smartphones are made of material that we find in our Earth. And to talk about these materials, where we will get them from in the future, what materials, and on what benefits? This is what applied geoscience is about. Just to let humanity thrive into the future. Yeah,
indeed. It's important on many, many levels. I mean, for example, my coffee mug right here. It's made of ceramic. And ceramic, for instance, is something where mineralogy is really involved in.
Yeah, I didn't like learning it.
Oh yeah, we had to write an exam where ceramics were ceramics were one part of.
Yeah, and I mean, we joked back then about it, but it's really interesting to see on what different daily things we see in our lives are actually influenced by this field, influenced by applied geoscience.
You talked about rare elements, for example, lithium. Lithium is everywhere. And to find lithium, you need to know which rocks to look at. And this is what they do.
Yeah, and how to get, especially if we want to talk about our influence on Earth and how we can minimize the effects that we have on Earth.
Indeed. These are just a few examples. And this is where we're at. You know, we started studying geosciences 3 years ago. And this is what you go through. This is what this first podcast is really all about. Trying to ramble a lot and in the process maybe show how complex this field truly is. You encounter chemistry of different natures, parts of biochemistry, geochemistry, parts of physics, parts of biology. And I think what I always find pretty interesting is where people end up after studying Earth/geosciences. You know, you can, as we've just said, you can end up in material sciences to produce coffee mugs, for instance. I mean, where would a good scientist be without a coffee mug, right?
The what I always think is funny is to hear the history or like the life story of the professors or of the people that work currently at our institute, for example, because very often they start at a complete different field and then just somehow, because of some reason, they end up in a very specific, completely new field of earth science.
I mean, I hope we're going to have him on here one day, but your professor, he wanted to become a veterinarian at first, I think.
I think this was his first plan, and then actually he started doing earth sciences, and he went on going actually applied geosciences. He wanted to look at at mining in general, and then somehow ended up here. Actually, there's something I can add here. There's someone called James Head. He was back then involved in the Apollo program, and he actually talked to us in our institute on a Zoom meeting because he's connected to my professor and to the people in our institute. And back then, this was before Apollo, he actually wrote his doctor thesis or his PhD thesis at this moment, and he was writing about stratigraphy and biostratigraphy, so paleontology and stratigraphy. And then NASA was like, yeah, we're searching for people that study the moon, geologists. So yeah, he wrote to them during his he wrote his his PhD thesis, and then they took him, and he worked at the Apollo program, and now is a very, very famous planetary scientist.
Yeah.
And it's a weird way to get there.
Yeah, and this is really cool because, I mean, you receive a very broad education here. I mean, to talk a little bit more about myself, I guess, I grew up in a small village. I was very involved with agriculture in my early years, actually until I moved to Münster. And, it would be pretty easy to transition into, lithology, I think. Trying to work on different kinds of soils, to work in an agricultural field. You could go into mining operations. You could do many different things because you just receive a very, very broad education. And this is really something wonderful. I mean, I think for every one of us, chemistry was pretty hard, but I wouldn't want to. I'm really happy I did it, because now I have a general understanding of chemistry, which I didn't have before, and which I likely wouldn't have if I wouldn't have had to go through chemistry classes.
Yeah, for me, there's probably physical chemistry. So we had to decide if we want to do biology or physical chemistry. Now, I loved biology in school, and this was one of my best subjects in school. So clearly, I decided to do physical chemistry. The physics and chemistry, which were these two subjects in school I was really bad at. But it was fascinating. It really was. It was really interesting, and it was a lot of learning, no doubt. But I'm so happy that I've done it. I've learned a lot, and my understanding of so many chemical processes has grown large. Really, I'm really happy that I've done this, even if these were two things. I mean, if you would told me that before studying, I would probably said no. No, I don't believe you, but here I am.
Yeah, that's the thing, you work, you know why you're doing this. You have a motivation to get through this because one day it's going to be a worthy tool, a very welcome tool.
Yeah, and earth sciences kind of gives the possibility to, well, join these things all together. Physical chemistry itself, I mean, is interesting, but now with my back knowledge in geology, of my back knowledge in earth sciences, it was possible for me to combine these processes. And suddenly I did understand things that I just have known before, and I've known that they exist, but now I was able to understand them. And this is the great thing that we have here, because again, all these different disciplines, and just suddenly everything makes sense when you put them together and try to explain Earth.
Yeah, and I mean, you never see Earth the same again. It's just, I don't really, it's a shame I don't remember the name of the professor in the documentary, during petrology, we once watched this documentary. On the history of geology.
The Scottish one.
Yeah, Scottish professor of geology. I'm really sorry, I don't remember the name right now.
I don't remember.
But I liked his quote. I like this quote where he said, "Never stop geologizing," because this is, it's you really can't stop this. If you've actually made a degree in geosciences, I think you can never again look at a landscape not wondering, why does this look the way it does? And this is something I enjoy a lot.
Yeah, and just I remember that at one point you had to learn for paleontology and for what is it called, like these classes of different animals.
It was systematic paleontology.
Systematic paleontology, right. And you had to learn a lot about corals and reefs, and you were a little bit annoyed back then because it was just so much information.
These animals don't even have a backbone. I mean, why would I care?
Yeah, and you just randomly stated a fact out of your book or out of your the things you've wrote, and you were like, yeah, I mean, see, now we have this problem here. Why is this interesting? And then we just looked at each other and we were like, yeah, but I mean, why? Why is this happening here? So we just suddenly were really interested into this one point for corals, which I don't know. I know nothing about corals.
The point being, there are pretty many small details you can discuss to no end. And that's really why we like to talk to one another so much, because I mean, on the one hand, oftentimes I come up with, a paleontological problem, and we can discuss this with mostly me talking, you asking questions, and it's often the other way around, like you telling me about planetary sciences. And somehow geology is always the point where most of our conversations are centered around, And I mean, just give us a landscape, and I think we will discuss about this landscape for hours and hours and hours.
Yeah, definitely. It's just this field allows to so many discussions and so many things that we can address, for example, in this podcast. Yeah. I actually started writing a list with things I wanted to discuss about at some point, and it's probably now so long that I will have content for the next year or so.
Yeah. But maybe on that note, you were talking about, basically looking at rocks in the Alps, where you figured out that, hey, these minerals are deformed in a certain way. They must have been part of a huge movement, of a huge chunk of rock moving a particular direction, turning around, and then actually seeing a structure in the mountain behind you. And I've had talking about never stop geologizing, I've had a similar experience down in Italy. Because, we were down there 1 week in the Piedmont Basin. The deposits there, they are of Cenozoic age, so, after the dinosaurs. And mostly this basin, the Piedmont Basin, was filled with all kinds of rubble. You are just south of the Alps, and all kinds of reworked material of older rocks were deposited there. Among them, some of volcanic nature, not volcanic, but magmatic nature. We found a sequence which didn't really seem to belong there. Our professor who led us through this little expedition, he always steered our direction towards one particular area having deposits which didn't really seem to fit. Everything seemed to coarsen upwards. The deposits had bigger and bigger and bigger clasts towards the top of the section. And here it was different, because some different units were in there, which definitely showed this could not have been deposited in the same place. And then one of the final days of this little field trip, he led us to a place where we could see a fold. So you could see the layers on top of each other, just, for the most part, being oriented horizontally, and then all of a sudden, a fold was visible right next to that. The deposits from horizontally, they just bowed down about 100 degrees, showing that some extensive deformation had occurred. And what actually happened at that place was that in a neighboring area, this huge chunk of rock had broken off. And it just started to slide into this basin where we were. And it started to slow down because it just essentially it rubbed along the bottom. It didn't float or anything. It just slowly drifted down into the basin. And while it slowed down, the front of this a locked-in unit, this not belonging there unit, it just became completely folded down. And this was, I mean, this, I'm talking on and on and on, but this was, I don't know, just a very, it was a very special experience to me because it really gave you an idea of the dimensions, because this was something you could see, you could only really see this fold on one place, but this was one huge chunk of rock which just had slid down into the sedimentary basin, so it was phenomenal, really.
All right, now we've talked about your weird little experience. But yeah, I mean, I get it. It's...
You could just cut out the half of it so that nobody will have to listen to me all the time.
Yeah, I probably will.
just get to the folding part.
No, I mean, but I get it. It's I often stand in these in front of these rocks, and then our professor or somebody else is explaining what happened here, or we try to figure it out together, and I always try to grasp it, but it's so difficult sometimes. And then later, when I'm like in bed or something like that, then I just realize the real influences or these real processes that actually created these things. We often stand there and talk like, I mean, most of the times here in Germany, we just are at our field trips, we normally find like sandstones, and we're like, yeah, so one new sandstone, here's a sandstone, here's a sandstone. And we talk about, yeah, you can see like the regression or the coming and going from the ocean in the stones, and yeah, all right, let's move on. But just thinking about seeing the movement of an ocean just in Germany, some 100 kilometers away from the actual ocean.
Yeah.
It's incredible.
It's like with the times. It's like with the spans of time we're talking about. It's you just become numb to it to a certain extent because you can't wrap your head around it anyway, so you just accept it.
Yeah, and I often have this feeling that it's very extreme in my field, planetary sciences, because I mean we look at pictures from spacecrafts that were launched from Earth to move through space to this planet or to our moon, and then we look at those pictures and just try to understand what we're seeing. I mean, just imagine trying to do stratigraphy, what you just explained before, on an image from space.
Yeah, that's
it. It is not only difficult, but you also lose some sort of perception, I think, and
I mean that's real.
Yeah, I often just have to really to think about this and to really understand what I'm actually working on.
Yeah.
That I'm actually working on the surface on the moon. Well, I'm not literally there, but yeah, you know what I mean. And sometimes I have to take my moments to really think about it, what I'm doing now, and just trying to imagine telling myself some years ago that, well, you actually work on the stuff you wanted to do. You work on the moon yourself. It's incredible. And sometimes I just have to address this to myself to really grasp it.
Yeah, and I mean, planetary sciences are pretty special in that regard as well. I mean, you've already touched on that you aren't physically there. I mean, you guys just can't go there, and you don't have a ground crew there. And when I'm thinking about trying to really figuring out how one place evolved over time, I can't imagine it without physically being there, without taking samples. And this is something you guys really... I think this is a challenge which needs to be addressed in the future. It would really be helpful to have someone there. I mean, you're trying to geologize, for lack of a better term, from pictures.
Yeah, and I'm working on the moon, and the moon is in this regarding, I don't like the word simple, but in some ways simpler than Earth.
Maybe more
Because
monotonous.
there are less processors going on larger timescales. But during the summer, I did an internship at the DLR in Berlin, so the German Aerospace Administration, basically. And I worked on Mars. And I tried to do stratigraphy, basically, from spacecraft imagery. And at some points, it was so difficult to wrap your head around it. And it seemed like so a simple problem. And I hopefully can talk about this in a later time. But it seemed so easy at first glance because, yeah, I know this topic from Earth and I can't go much into detail here. But then trying really to understand it from imagery data from spacecraft, at some point it just blew our minds and we couldn't wrap our heads around it. And just with spacecraft data, this is really difficult. For that, well, I just wish that at some point in the future, it's hopefully much easier for us to visit these places and to try to understand them.
Oh, absolutely. I mean, there are places where it seems pretty unlikely. I would say Venus. I mean, trying to get to the surface of Venus to take samples, and let's not even talk about working there. I think it's really...
But the atmosphere.
Yeah, it's really challenging to go certain places. Mars certainly seems to be the next place where we will go, but I mean, the question remains, how long can people actually be there, work there? And that's really interesting.
Yeah, it's a topic for itself.
Yeah, I mean, it's really interesting because where's geoscience going? In planetary sciences, we can definitely see that there... I often like to think that right now we're in an age where we're growing up in science. You know, we are trying to grasp that to truly understand other planets, we need to go there, at least from a geological perspective. But also back on Earth, geoscience is going to be a very important field in the future, because...
Before you move on this topic, there's actually something I want to address here, add here. And this is a quote that my professor back then said, I think, in one of our first planetary science lessons. And, you know, some people asked actually me this question too, which was, well, we were on the moon. Well, why do we have to go there again?
Oh, yeah.
Why do we have to go to the moon again? And then, well, the answer is just try to imagine that that you're not from Earth. You're an alien visiting Earth. And you can land, and there's only let's say you can land on 6 different spots on Earth. And then you can let these spots just move in a circle, an area that's about 2 kilometers large, and you can just look at the Earth at these 6 spots. Now just try to imagine the many things you won't be able to see. All of the Earth is so variable, and just in these 6 spots you couldn't grasp anything.
Yeah, I mean, Earth is special because Earth is that diverse. I mean, me being a naive, aspiring paleontology student, I would say other planets are more monotonous to certain regards, but from a geological perspective, I mean, for instance, we know that Mars has been way more dynamic. That there was at least some kind of water, that there were dynamic sedimentary processes. So yeah, indeed, from the perspective of geological exploration, it's mind-blowing to just think we can go there, observe a very, very tiny speck and grasp the whole picture.
I just hope for a good future in this field. Not only for me because I want to work in this field, but also just because it's so interesting. And I don't know, just imagining that we kind of are trapped on Earth and we don't look out what else is there.
Yeah, that...
I don't know, just kind of makes me sad.
Yeah, that's the thing, you know, I tend to say we can't really understand. I mean, oftentimes people come to me and ask me why am I interested in extinct animals, and my answer usually always is, I don't know. I just like them.
Because they're not annoying, they're dead, they don't ask stupid questions.
Yeah, then again, my tarantulas aren't asking stupid questions.
Yes, that's right. Correct.
Yeah. You know, the thing is, there is the easy answer, I just like it. There is the answer that I love animals and that I think there is nothing more interesting than animals. But maybe the more diplomatic answer would be, we can't really understand our place in something if we don't look at something else. We can't really understand how our system on Earth right now works without comparing it to to past times. We can't, you know, it helps because we can verify that certain things we observe today seem to have been like that ever since animals appeared. And this is something I would really see in this as well. We know that about Earth, we know certain aspects about Earth, but we keep coming back to this point that Earth is pretty extraordinary in many regards, and we wouldn't know that by not looking at other planets. In planetary science, it's kind of a topic to talk about Venus maybe being an example for an extreme hothouse climate, for maybe a future of Earth if things go very terribly wrong here. I mean, but I hope that people out there will understand what I mean. It helps to understand something if you look at something else and you try to figure out why did it go differently in that case, or why is it the same in that case. So we
trying to see the bigger picture.
Exactly. We can't just lock ourselves down here, and I mean, we can choose to ignore everything, but this doesn't help. We need to accept that we live in a very dynamic system, that we are a part of it, and one day we are going to feel the consequences of that, because we are really changing the place we're living.
Yeah, I mean, you already feel that. I mean, you just have to look at temperature data from the last 100 years or longer, and there are changes that already happen and changes that we already experience now.
Exactly. And that's the thing. That's what I think that's a very important part of why I personally think that this is a field for the future. And this is why I think not only planetary sciences will undergo changes in the future and will have a future, but this field in general, we need people to help coping with the problems we're going to face, because world is changing and there is no way stopping that. It's going to keep changing because that's what we see in Earth's past. While maybe we could say changes stayed within certain borders, it changes all the time.
Earth is not made for us.
Exactly.
It's not that Earth is made that just perfectly fits us for every time. No.
Exactly.
That's not how it works.
Exactly. We developed in a certain period of Earth over a certain time, and that's why extinctions happen. That's why we see these major shifts, because, I mean, extinction and evolution, it's something that is going on all the time, everywhere. But this is why we see certain cuts in the history of life, because some organisms couldn't change during times where change was very, very rapid. And we are undergoing a period of rapid change. How rapid? I mean, no, this is... I don't really want to get into too much political stuff right now or anything, because that's honestly something I don't really know enough about. But
yeah, but then also climate change is science, and we tend to politicize climate change. But I always think that this is kind of the wrong way. We can do politics about what we want to do and what we want to, what our ideas to work at this topic. But in the end, climate change itself is a scientific topic, as every other topic in earth science too.
Yeah, and it should be regarded as a scientific topic. I mean, of course, politics, it's our way trying to deal with these problems, but I think too many times we try to see it through this political lens, and we need to essentially try and better understand our world, and we need to better understand the changes that are going on right now. So
yeah, definitely.
I mean, our sedimentology professor, for instance, he once stated that there are, I don't know when, I think it was right at the beginning of, it was one of our first courses, where he said that geoscientists are going to be needed in the future from his perspective. I mean, it's easy to say that when you're in that field, but yeah, you know.
Yeah, I mean, I would support that.
Exactly.
Definitely. I mean,
I think my audio just lagged a little because my laptop activated its... What's the English term? Bildschirmschoner.
Screensaver.
Yeah, screensaver. Yeah, so I think that maybe that's a little element we could introduce right here. Maybe we could introduce some German class. So, you know, a little section where we just introduce some nice little German words to our listeners. Not the boring ones.
Let's just start talking German at some point.
Yeah, maybe we could do that. But I mean, I don't mean the boring words, you know? I don't mean the words like Schadenfreude, which these words everyone knows. I mean, like, really the nasty ones.
Yeah.
Klebstoff.
Yeah, it's a nice German word.
Glue. So yeah, but back to the future of geosciences.
I mean, it depends, I guess, on the field. There are some fields that are, it's difficult to say, but maybe not, they don't contribute that largely to, I would say, problems that we'll face in the future, but I don't think that I don't think that they are less interesting because of that. If you know what I'm trying to say here, then be really careful.
Oh, yeah. I mean, vertebrate paleontology, hey.
Yeah, I don't want to say it. No, you said it. It's okay.
So, you know, I mean, yeah, let's face it, for the most part, it's really self-sustaining because it's a very self-centered science. I mean, you could be generous and say that, as I've stated before, to understand our ecosystems today. We need to understand ecosystems throughout the ages. But for the most part, people who are interested in vertebrates, vertebrate paleontology for that matter, are mostly interested in animals. I mean, I'm just a naive young student who probably doesn't really know what he's talking about, but that's at least my perspective on things. It doesn't mean that it's less interesting, but I wouldn't really deny that it's very, very self-centered. I mean, planetology is to a certain degree as well. I mean, you don't really have a direct outcome from that. You don't have a direct return, like for instance in material sciences, which crystallography and stuff is a part of. But that's really the question. Do we want to try and keep understanding the whole system, you know?
Yeah, I think it highly depends on the point of view you have on science in general, but to defend vertebrate paleontology here, at this point, we are not just talking about the history of Earth, but the history of ourselves. This is the history of life.
Yeah.
This is where we came from. And I think understanding our own roots and why we are even here, or evolution as a whole process is, I think, for me, it's always kind of a must do. We just have to do this because, I don't know, it's just, I love the, I think Carl Sagan said it, but I also think, I think it's from Carl Sagan. He always said that, no, it's not from Carl Sagan. Wait, very famous physician. Yeah, nice German here. Physician.
Physiker.
Very famous Physiker. Always in the news from Cosmos, the Netflix, or the, not only Netflix, but the TV show.
Everything well planned out, you know. We've got our quotes ready. Everything is top notch.
Yeah, we have many plans and structure for this podcast.
You mean the bald one?
Yeah.
Screw it, because
Tyson?
No, I've actually talked about him a few days back.
Because of some Neil deGrasse Tyson. Man,
no, he's not bald.
I just thought about Mike Tyson.
He's not bald.
No, he's not bald. Yeah. All right. Yeah, he has some hair. Never mind.
Not to disrespect any scientists out there. I don't know. At least I have the excuse that I'm very bad with names.
Yeah, me too. And because of some reason, all in my mind was Mike Tyson, and I thought, no, he's not a famous scientist.
No.
Right. So it's a Neil deGrasse Tyson quote, and he always, what he said was that we are not sharing this universe. We are not living in this universe. We are part of it.
Yeah.
The materials we are made of, the carbon atoms in our bodies, are the same carbon atoms that you find in, I don't know, your wooden desk or your stone in front of your house. These are the same carbon atoms that were formed billions of years ago in the core of some sun or from some star, I have to say here. And I mean, we are part of this universe, and we are actually part of a universe that is self-conscious, and a part of the universe that can see itself. And just from this point of view, we are able to try to understand ourselves. And just this simple fact just makes me so sure about this, makes me so interested and so fascinated about science at all. And I don't know. I guess it's a point of view, and I know that not every person is sharing this point of view, but
yeah, no, but
it's one of the reasons I became a scientist, or I want to become a scientist.
Yeah, I mean, where you just talked about him, he also has this nice quote that once he passes away, he would like to be buried in earth, to be devoured by the worms, to be feasted on by the creatures in the soil, as he feasted on the products of earth during his life. And it's a pretty beautiful quote. I mean, I see it very similar to your point of view, because we are in a part of this entire universe, and to maybe come back down to earth with this line of thought, when
we kind of get carried away.
Yeah, but I mean, that's what we're here to do.
Yeah, true. Earth science is it's our topic.
Yeah. You know, we can, that's why, or that's one of the points I always try to make as well. We can decide to ignore evolution. We can try to, or we can, of course, it's, from my point of view, it's perfectly valid to say vertebrate paleontology is something which is really self-centered for the most part, maybe, but it's our history. You know, I'm very interested in dinosaurs and pterosaurs, which is not the line from which mammals and at last we evolved, but you know, it's, once again, it's trying to see the whole picture, to see why have we evolved a certain way and why didn't other animals? Why? I mean, we don't know. Maybe it happened. I would say it's very unlikely, but maybe there were intelligent dinosaurs. Certainly not to a degree we are, but it's just, you know, why didn't they evolve into what we evolved into? And I think it's important to study this, because it can also be very humbling, because you can have, I think you can gather a certain amount of respect for life in general when you try to understand how much of a coincidence and our evolution truly is. I mean, I would say intelligence hasn't happened before, maybe because it's just unnecessary. Maybe it's just because it just isn't that necessary to stick around on this planet. And I don't know, to me this always instills this feeling of happiness inside me, because it's very unlikely that we're here at all. And I wouldn't know this without paleontology.
Yeah, I completely support this. I know that there are some people, or I think that there are actually many people that will think that this is actually a very sad fact, but for me also not, because for me this just lets me appreciate life more than, you know, yeah. Can I just address that I love the fact that we tried to defend vertebrate paleontology and ended up discussing the very fundamental of science.
Yeah, but well, I mean, again, first podcast, and I don't know, so far I enjoy it, because this is really what we want to do, you know. We would like to go in deep with these topics, because this is what it really means to us. We really want to center everything around geology, because it's just the field we're most interested in general. But we like to talk about scientific basics, you know. Why do we think that science is important? Why do we think that the way we are addressing science at the moment, why is the way we are making science at the moment? Is this a correct term? Damn it, I messed up. But you know, why do we really believe in the way we are addressing science currently? How we are going about science currently?
Yeah, and I think this was a lot about rambling about science there. But this is what you can expect, I guess, from this podcast. And this is, like Dennis said a moment ago, why we actually wanted to do it. It's basically just us ramble. I mean, it was really unorganized today. And we will have specific topics in the future that are not as broad as Earth science. But still, it will be, I guess it will be a lot of rambling and us just trying to, I don't know, just trying to
wrap our heads
explain to us different topics of our fields. Yeah, this was the other thing I wanted to say. And it is actually very difficult to start this, and we had a lot of problems in this process because talking to ourselves, like sitting on your balcony with a nice glass of gin, for example, is very easy. But I guess the moment you just click on recording, it changes everything.
Oh, likely this is gonna be the one where, I mean, hopefully we are planning this long term. We are planning this to be our to be our introduction into SciComm. And I guess this is just gonna be one of those episodes where you go back to in a few years down the line, thinking, what the hell were we doing?
Yeah. And also, you know, we are at the moment still undergraduate. No, I'm not doing this mistake again. We're still undergraduate. And I mean, I will be in master the next month, I guess, hopefully. But we are not trying to play scientists here. We are not trying to say things that we don't understand. We really want to give just our point of view, or just this student point of view that we have at these topics, and science at all, the science progress, at the science theory, and science, or just general the work in science. And I think our way into science, or we can just kind of like a diary of our way into science.
Indeed,
hopefully.
Just ride along with us.
Yeah, and I guess this could be maybe interesting for people that are already in science, if you kind of want to look back at what you were before.
Oh yeah, man.
Or just people that want to join science.
I expect all the big names in the audience.
Sure. From day one.
Yeah.
Yeah, I mean, probably for the first year, I will already greet our one listener that is here after the end of the year.
Yeah, exactly, and probably it's going to be one of our best friends anyway. No, but just not to completely ridicule all of this. This is really just we don't know. We hope for the best, of course, but we will see. We will see where this leads. We will see whether people like this, and if people don't, then we will just try something new, or try to better ourselves.
Yeah, and we will hopefully, grow into this and can educate ourselves and I don't know, starting becoming better at it.
I will be a better person. Write it down 100 times.
Yeah. No. seriously, I'm not going to do this. Anyway, I think we can end this first episode here. Is there something you just want to address to this end of this podcast, or?
Yeah, I really just would like to sum up for me personally, because while we've been meandering a lot, we really enjoyed our time making our bachelor's degree. I mean, we're still making our bachelor's degree at the moment, but we enjoyed the courses. We came into this with a specific goal. We found our love for a lot of different topics in this whole field of science, and I hope that people will join us, that we hopefully are able to convey some of our enjoyment and our fascination for these topics. And yeah, just thanks for listening. If you made it to this point, really, I'm absolutely, totally blown away that you've made it to this point. Because, I don't know, it's our first podcast, and
it was weird.
It was weird. It was an experience, I would say. Something completely new, and yeah, I'm really thankful. If you made it to this point, thank you so much.
And now a word from our sponsor. No, I guess I just support everything that Dennis just said there. It was really nicely said. And with that, I guess we will end our third podcast. Have a nice day, evening, or whenever you're listening this. And probably if you listen to this whole podcast, there are many things you can do that maybe are more productive than this. Anyway, have a nice day.
Bye.
Thanks for listening to the RockyTerrain podcast. If you enjoyed listening to us, please consider subscribing on your favorite podcast platform. Everything addressed in this podcast reflects our own opinion. You can contact us at 4.5gainthemaking@gmail.com. That is 4.5gainthemaking@gmail.com. All music used is from Kevin MacLeod and was downloaded from filmmusic.io under the Creative Commons license. That is heavy interlude for intro and outro, and home bass groove for intermission.
I mean, that's what we're here to do.
Yeah,
rausschneiden.
Earth science is it's our topic.
Yeah.